This is going to be a fun one, I hope. We'll see how it goes. It's all very new, so welcome. And hi, everyone. And oh my God, it's JavaScript Day. And my name's Craig. I'm from New Zealand. It's pretty early for me, but I'm so happy to be here. Hope to catch you up with some questions in the chat later. But first off, I have to kind of confess something. I miss university. Not like enough to go back and do a PhD or anything, but I miss learning about weird stuff. So today I'm going to talk about some weird stuff and put my little university hat on. This stuff is probably a little bit more relevant today than it was when I was studying, but it's still also fairly academic. We're going to get a bit mathy. I'm going to try to talk about the practical applications maybe, but we'll see how we get on. And I'm referring, of course, to React. Kidding. Although I love their logo, we're actually going to talk about quantum computing. And so obviously this is a pretty big, pretty technical topic, but we're going to try to cover some of the core concepts, including quantum state, pretty important in any kind of computation, quantum measurement, so how we can find out about some quantum state that we've produced, quantum gates, so trying to manipulate a quantum state, kind of like we do with logical gates in a binary computer, and quantum algorithms. So we'll talk about how some of these things get used.
Message from unknown. Wow, you really do just put the word quantum in front of everything.
Huh. What?
Message from unknown. Go to your computer, Craig.
What is happening? I guess we'll go to our computer. Huh. Something's going on. What is that? Huh.
Message from unknown. It's Scott, and man, whatever. Hey, I need your help, Ant.
What is
Message
this?
from Scott Lang.
I'm in the
Hurry
middle
up,
of
it's
the
important,
talk.
Ant.
Please. Okay, what's going on here? This is fine. Let's see what's happening. Cool. Okay, we're going to talk. What's going on? Okay, I guess we're getting some messages from someone and they're touching our computer and I don't know what's going on, but we will just keep going. It'll be fine. Okay, quantum state. Let's focus in on this. So in a classical computer, a bit can only exist in a binary form, so in a 1 or 0. We're representing a binary state, and that's typically represented physically as like high or low voltage, or an on or off switch, some kind of magnetic orientation on like reading a disk. And if I have n bits, I can represent exactly 1 out of a possible 2 to the power of n states. If I have 2 bits, I can produce 4 states, and so on and so forth as I get more and more possible states. But I can only ever represent 1 of those states at a time. In a quantum computer, I have what's called a qubit. And a qubit can be in a combination of 0 and 1 at the same time. It's a representation of quantum state. This is the idea from the famous Schrodinger's cat thought experiment, where you have a cat stuck in a box, and if some random atomic event happens, the cat will be fatally poisoned. Until we look in the box, the cat can be considered both dead and alive. And the technical term for this is what's called a superposition. By using a superposition, I am talking about probabilities. So the probability that a qubit will be in a given state. And by using superposition, not only can I represent those 2 states, I can represent 2 to the n states simultaneously. The more qubits I have, the more states I can represent exponentially. And this is the key insight that makes quantum computation fundamentally different from classical computation. We use some special notation to represent quantum states. You've already seen it in this slide. It's known as Dirac notation, where we have things called bras and kets, which represent a different part of a quantum state. So here what we're saying is that some ket called psi is a quantum state where there is an alpha-sized chance that it is in the 0 state and a beta-sized chance that it is in the 1 state. Alpha and beta in this situation are called probability amplitudes. And just to make everything a little bit more fun and a little bit more mathy, these are all complex probabilities, meaning that the probabilities are numbers that contain a real component and an imaginary component. We can think of these kind of complex probabilities as a coordinate position that exists somewhere within a circle of radius 1, centered on 0, 0 on the unit circle. And so a ket is made up of 2 positions within that circle. As a first example, we can look at 2 positions. So at 1, 0, so right at 1 on the unit circle, and 0, 0 right in the middle. These 2 positions are whole numbers. They're 0 and 1 fundamentally, but they can be expressed as complex numbers, even though neither of them have an imaginary part. And we can use this constraint that we have on the right-hand side, where alpha, the absolute value of alpha squared, plus the absolute value of beta squared have to equal 1, so that they sum up to one whole probability, that 0 to 100%. In this case, we have 1 plus 0i squared plus 0 plus 0i, the absolute value of that squared. And we can compute those that they both equal to 1 and 0, and therefore this constraint is valid. This is a valid quantum state. For an example with some imaginary components, we can look at 0, 0 and 0 minus I. Now, again, we can represent these coordinates as complex numbers, but now our beta value has got an imaginary component. If we take the magnitudes again, so that's what we're doing, we're taking the magnitude of this position by taking the absolute value and then squaring it. Again, we get 0 and 1, so they're flipped around this time. So what we're saying here is that there is, for these 2 sets of coordinates, there is a probability of being in a 0 state of 0, and the probability of being in a 1 state is 1. So we can say that we pretty much definitely are going to be in a 1 state. And in general, we can say that if our coordinates lie on the unit circle, on that around edge of the circle, it's going to produce a definite outcome. So 1 being in the 0 state or the 1 state, so not a superposition. And because we have that 1 value on the unit circle, our other coordinate must be at 0. In this particular case, we have a qubit that is basically behaving like a classical bit, but that's not particularly interesting. As I mentioned before, so most of the magic of quantum computing comes from this superposition, where a qubit can be considered to be in multiple states at once. That's to say that the probability that a qubit is in a given state is not 1 or 0. In this case, if we have 2 coordinates at 1 over the square root of 2 and 0, and another one at 0, I over the square root of 2, if we compute these probability amplitudes, we're going to find out that we actually have a probability of being in either the 0 or the 1 state of 0.5. We don't know which of those states we're in. This quantum state can actually be represented as a column vector, so 2 little numbers like this. And to keep things familiar for us, we can also just use a regular old JavaScript array. It's a couple of values in an array. But because we need to be a little bit more specific, we're going to add a representation for complex numbers. So we have this complex function, and we pass a real value and an imaginary value, and we get some interesting number out of it. The key point here is that a quantum state is probabilistic. With a classical bit, we can tell that a state is either 1 or 0. With a qubit, we don't know what the state is until we measure it. Here we have a kind of more complete representation that we're talking about here. So we have a function that takes a complex, a real and imaginary number, returns an array with the 2 values in it, and we have the ability to make a k0 and a k1. So that's a ket that is definitely in a 0 state, or a ket that is definitely in the 1 state. We can think of either of those kets as a part of a complex qubit.
Message from Scott Lang. Oh cool, maths. Okay, here's the deal. I'm locked up in the quantum realm, and I need you to help me get out and...
Well, that explains a little bit more, I guess. Okay, we've got Scott Lang, we've got Ant-Man, and we have to save him again.
Message from Scott Lang. Someone knocked me out, and I woke up in a prison cell and... Message from Scott Lang. But I accessed the system that controls the locks, and entangled myself with your CPU. Message from Scott Lang. So I can send you messages and run code and...
Huh. Okay, I guess this is explaining a little bit more. Huh.
Message from Scott Lang. Shit, someone's coming. 1 second.
Okay, I guess we'll keep going. So quantum measurement is the part where we actually look inside a box to see the cat. When we measure a qubit, it collapses into one of the possible states based on the probability distribution of these states. In this case, the probability of getting a zero state is 1. So in a binary system, we know which type we're going to get. If I've set it to false, I'm always going to get false. With qubits, it's a little bit different though. I have to do things like normalize my product so that I don't have any values that are outside of those the possible probabilities. And when I actually want to measure it, I have to account for each of the individual probabilities that might make up a given state. I need to be able to look through every value that exists in my qubit and figure out which one I'm actually in at any point in time, at least when we simulate it. And this is kind of what that would look like in a little bit of JavaScript. But let's talk a bit more about measurement. So here we have a qubit that is definitely in a zero state. So we have a probability of 1 that it's 0 and 0 that it's 1. We can represent that with this array here. And we have some of these alpha and beta values again. And again, we can see that if we're in a 0 state, we've got a probability of 1 or a probability of 0 that we're in the 1 state. We can measure this in a few different ways, and we're going to see that every time we measure it, we always get a 0, which makes sense given the probabilities that we have. In a slightly more complex example, when we want to convert our complex amplitudes into probabilities, we have a 50-50 chance of either 1 or 0. That looks a little bit something like this. Again, with our alpha and beta values, we have probabilities of 0.5 for either position, or either state, 0 or 1. And so if we were to measure our ket 6 times, we would expect half of them to be 0 and half of them to be 1. Again, this is probabilistic, so that might not actually be the case. It's like flipping a coin. You could measure 0 10 times in a row. We can expand this to a system with multiple qubits. So if we have 2 qubits, then the probability of getting a 0 state is 1 over the square root of 2, and the probability of a 3 state is 1 over the square root of 2. Then we have a 50-50 chance of the state collapsing to 0 or 3, and a 0% chance of the state collapsing to 1 or 2. So we can read our state non-deterministically, as I've said, but how do we change state? Oh, here's one more example of this is where we might only want to care about a specific qubit. So in this case, we've got a 2-qubit system where the probabilities of getting 0 or 1 are 0, and the probabilities of getting 2 or 3 are 1 over square root 2, which again converts into 0.5 probability. Sometimes we don't care about that second qubit though, and specifically in some of the algorithms we're going to talk about. And so if I was to ignore everything after the first qubit, I would only measure the first qubit and I would always get a 0 back. That's going to be important a bit later. The ignore function looks a little bit like this. Again, don't worry about the implementation too much, but it's basically saying, don't worry about everything that comes after the first qubit.
Message from Scott Lang, Craig Ant.
Oh, more of this.
Message from Scott Lang, Craig Ant.
Yes, Scott, what's going on?
Message from Scott Lang. I've made some progress. I've got access to the quantum security system computer and...
Huh, I guess that's a good thing. Maybe he can help himself get out.
Message from Scott Lang. Darn it, there's 3 layers of security to get this door open and...
That doesn't seem good. I guess once more, we're going to just keep going and see what happens. Cool. So we have these states and we know how to measure them, but we want to do some stuff with them. In a classical system, we know what gates are. We're applying a binary operation to a binary state. We have an AND, where if we take 2 bits and they're both 1, we get a 1, or an OR gate, where if either of the bits are 1, we get 1. The exclusive OR, where if it's only one of the 2 bits is 1, we get a 1, or a NAND, which is an inverted AND operation. We always get a 1 unless both of the inputs are flipped. With quantum gates, it's a bit more complicated. We want to apply a matrix operation to a quantum state. 2 common gates that we're going to use are the identity gate and the Hadamard gate. With an identity matrix, we can see here we have this identity matrix with this 1, 0, 0, 1, and we want to apply that to our 0 state, where we know that we're going to get a 0 out. The identity gate does nothing. It multiplies the 2 things together and returns the original result. And so we get exactly what we started with. The Hadamard gate is a bit more fancy, and it's kind of where half of the magic of this stuff comes from. That's out of order. Cool. With a Hadamard gate, what we're saying is we want to apply this gate to a qubit, and we're going to put it into a superposition. So we take our gate from being in that definite 0 state, we apply the matrix math to it by cross-multiplying the matrices. Don't worry if you don't know what that means. And we end up in a superposition. With our little helper functions, we can do some stuff like this in our kind of JavaScript simulated land. So we have some matrix called Hadamard, and we have some ket called 0, and then we perform some operation on them to manipulate them. Again, this is just matrix operations. We can just treat them like arrays and move stuff around. In this case, when we were to read our numbers out, we get that we have this superposition state. So we have 1 over the root of 2 chance of being in the 0 state or in the 1 state. Again, a 50-50 chance. As the number of qubits increase, though, so does the complexity of these expressions. So if we were to do a Hadamard operation on 2 qubits, we have to do what's called a Kronecker product, which is, again, some pretty fancy maths. But we've already done one of these, and so I think it's going to make it a little bit easier to explain what's going on. This Kronecker product is the product of a 0 ket and a 1 ket. Here we're saying the first one Hadamarded with the second matrix. And in some JavaScript code, what you can see is all we're doing is we're taking the direct values of the first and multiplying it by the second. This is kind of a dumb, it's called a tensor product. So not a full multiplication of 2 matrices, but just a light kind of in-between multiplication. And when you have bigger matrices, the stuff gets even more complicated. But thankfully, with a little bit more code, this stuff actually does generalize to a matrix of any size. And we can do the proper multiplication as well, which we're going to need in a second when we do some more algorithmic stuff. Oh, more of this. Okay.
Message from Modog. Oh, hi, Craig. It's Darren. I have Scott. Message from Modog. He's never getting out of here.
I guess we need to save Scott properly now. Okay. What's going on? Oh, Cassie. Hi, Cassie.
Message from Cassie Lang. Craig, it's Cassie, Scott's daughter. Message from Cassie Lang. We've figured out how to open Dad's cell. You need to run some quantum algorithms.
Cool. Okay.
Message from Cassie Lang. It's Deutsch Jossa, Grover, sure, in that order. But we don't know the inputs.
Okay, cool. I guess we're going to see how this works. Let's talk about some quantum algorithms. So the Deutsch algorithm solves a problem that isn't particularly difficult or particularly important, but it can be solved faster on a quantum computer than on a classical computer, which is pretty interesting. It simply says that if you have a function that maps from 0 and 1, 2 inputs, to 0 to 1, we want to find out if that function is constant or balanced. So if I put 0 in, do I get the same thing as when I put 1 in, or are they different? In a classical computer, it's pretty straightforward to do this thing. So we have a function that starts and always returns 0, a function that always returns 1, a function that always returns x, and a function that always returns 1 minus x. If I pick one of these functions at random, I have to evaluate the first function with input 0 and the same function with input 1. If they're the same, it's constant. If they're different, it's balanced. A classical solution to Deutsch requires inspecting the oracle twice, once with each input. The quantum implementation of this is a little bit more complicated, but more interesting. So we're going to have an initial state with 2 qubits and a Hadamard gate for 2 qubits. We apply the Hadamard gate to get a superposition, so the state where all the possibilities are possible. And we have some black box oracle matrix. So this is the input that we don't know about. We don't know what this function is. This is the answer that we want to find out. And we apply that to our superposition state. We then take just the first qubit of our superposition state and apply a Hadamard gate again to that state that we had. And then we measure the first qubit of that state that we've got. Because the second bit contains redundant information about phase and stuff that we don't care about for now, we're going to get the result out of the first qubit. If it's a 0, we know the function is constant, and if it's a 1, the function is balanced. So here's a kind of implementation using our sort of semi-implemented JavaScript simulator. And as you can see, it's kind of a lot of work compared to the classical approach. So what's the point? In this case, the quantum solution actually requires inspecting the oracle just once. Remember, we had to do it twice in the classical case. But with the more generalized version of the algorithm is where this gets interesting. So this is generalized for bigger inputs. So if we have a function where there's n number of inputs, all are 0 and 1, if they all equal 0, it's constant, or all equal 1, it's constant. And it's balanced if half of the inputs have 0 as the output and 1 for exactly the other half. In the classical version of this, we have to inspect the oracle 2 to the power of n times. So it gets very slow very, very quickly, especially if you don't know what the function is and how long it takes to operate. But in the quantum situation, we do have some bigger matrices, and we have an initial, and even just the 3 qubit state, you can see how these get pretty crazy. We have a Hadamard gate for 3 qubits. And then we're going to apply that. We're going to get a superposition of all those 3 qubits. So that's 8 possible states. And then we're going to have some oracle, which is even bigger. It's going to be 2 to the power of n. So in this case, 16 by 16 matrix, so pretty memory intensive. And the size is going to increase exponentially with the number of qubits. We can apply that to the superposition state, read just the first n minus 1 qubit to the Hadamard gate, apply that gate to that state that we had. And if we then measure the first n minus 1 qubits, we get rid of that redundant information. If we have 0, 0 as our state, we know that the function is constant, and any other state, we know the function is balanced. Again, in our kind of simulated code, we start off with some oracle that we don't know about. We set up some initial state. We run some gates. We apply the oracle. We run some more gates, and we measure the outcome. In this case, the quantum solution still only requires inspecting the oracle 1 time, much faster than the classical version. Let's run the algorithm and see what happens.
Message from Scott Lang. That worked. The first lock opened and...
Awesome. We got the first lock open. Okay, let's go on to the next type of algorithm. Cool. So we have Grover's algorithm. Grover's algorithm finds a marked item in an unsorted database of n items. You can think of this as kind of like a quantum search algorithm. In the classical case, this requires Grover's inspecting every item in the database once. So it's not particularly efficient. But we have a quantum version of this algorithm too. So this example, we're going to use 2 qubits. But they're in a different initial state than the Deutsch algorithm. So we have 2 0 qubits. We again have the Hadamard gate to apply a superposition, again, where most of the magic comes from. And when we apply that to our initial state, we get this superposition. Everything can happen equally likely. In this case, we have oracle for a search function, which returns the value 2. Again, we wouldn't necessarily know what this input was going to be. We apply the oracle to our initial state. And then we apply a special diffusion operator, which is a fancy operator made up of multiple gates and ends up in a matrix looking something like this. We're going to apply that diffusion operation, the square root of n times approximately, and it's going to pop out that 2 has the highest probability. This is not going to be a definite result. These are probabilistic. You could still get the wrong output here. Much of the research into these algorithms is about how do you maximize that probability? How do you retry this if you don't get the answer you expected? And again, to run this in our simulation, we have to do that thing in our JavaScript code. So we set up some initial state. We apply the initial transform to get into the quantum superposition. We then run the quantum algorithm square root of n times, again, much more efficient than the non-quantum version. And we measure the state at the end to find out the result of our search. Let's see if we can run Grover's and get some more locks open.
Message from Cassie Lang. Nice. The second lock is open.
Nice. That's awesome. Okay, one more to go. This is the big one, prime factorization. In a classical system, if you have 2 prime numbers and you want to figure out, multiply together, and you want to figure out those 2 prime factors of some big number, it's going to take you approximately O of the square root of n. Most encryption works on the fact that this scales pretty badly. We're going to take some number, in this case 391. We're going to divide by every possible number up to the square root of n to try to see if anything is a factor. If we find those 2 factors, we'll have the result, and we can log those out, 1 and some, or whatever those 2 factors are. The quantum version of this efficiently finds non-trivial factors of a composite number n by applying this quantum transform. So a to the x mod n, and then figuring out some period of the cycle within that, and then applying a greatest common denominator onto that transform. And it's able to do things like this pretty much instantly, and for much, much bigger numbers, causing pretty big issues for most modern cryptography. In our kind of JavaScript-y version of this, it all looks a bit more insane. So we start by picking out some initial value. We're just looking for something that is not already a prime number, a prime factor of our search number. And then we need to set up our initial state. This is pretty big. We end up with n times n number of qubits that we need to perform this operation, which is why we're kind of safe for now. A modern quantum computer can't actually do these things yet. We're going to apply some initial operations to get into that phase state that we're looking for. This is that first chunk of the operation. And then we're going to apply a quantum Fourier transform. By running it like this, we're going to get some estimate of the period, and we perform that mod x. And from the output of this, we're going to be able to factorize our prime number into 2 things in pretty much instant time on a quantum computer. So let's run this. And looks like we've pissed off Mr.
Message
Modog.
from Modog. What? How are you doing this?
Cool. We broke all the locks. Everyone's out. We solved some quantum algorithms.
Message from Scott Lang. I'm out. Thanks, Craig Ant.
You're so welcome, Scott. I'm glad you're safe. And in the fast version of this, that brings us to the end. So that's a pretty high level, pretty intense little run through of how some of these quantum algorithms work. It's very impractical. We're a long way away from having any kind of computers that can run any of these things, but I think it's really interesting. And like I said, I really like learning some weird stuff. Cool. Thank you so much. I hope that was useful.
It's 2:30 in the morning, 2:45, and you decide to kick us off with quantum algorithms and explain it in a cohesive approach. I was like, yeah, that kind of makes sense. So
I think that's kind of the thing, is that it kind of makes sense. It doesn't actually make sense. Writing these kind of talks is so complicated, but I think it's really interesting. I like the math part of it too. I don't feel like we get to do that stuff enough.
That's true. I love how you still brought like a little bit of humor and wit to your slides and funny animation. That's always what I like about your talks. They're always like, there's a level of detail that you just pay attention to make it interactive. And I like that.
I do love a slideshow.
You won't believe this, but we have a question.
Let's see if I'm even qualified or capable of answering it.
Yeah, Paul, why don't you hit the
compile time? Good question.
So let me just read this. It seems like we're moving the checking from runtime to compile time. Kind of, yeah. So it's a really interesting point. So none of it is like compile time is not really quite the right idea there. It's more about you've got to think of this as a physical system, right? So we've got physical atoms or whatever that thing is that are in a quantum state. And then we have all this machinery around this thing that is going to do some measurement on the thing. So the complexity is, getting a machine in the state that it can do these operations, right? If you can get the machine in that way, it's going to be really efficient at doing this thing. It's almost like the uncertainty principle, right? Like you can't measure the velocity or the position of an atom at the same time. That's where a bunch of the stuff is. It's a trade-off, right? So we get all this efficiency and complexity in time, and we have all this additional like mechanical complexity of actually making this thing run. The theory is much more interesting to me than how you actually build one of these things, because we're still a far way off.
Indeed.
I don't know if that answered it, but
I'll just accept this as an answer. That's also what I did with your talk most of the time.
I just lied for 30 minutes. That's exactly what it is.
Fair enough. So, in the scope of quantum computing, it's very limited right now. So, what do you think is the probability of this changing at some point?
I mean, people are researching this stuff right now. Obviously, these algorithms, like I think, like 1996 is when I think Shaw's, I can't remember if Grover's or Shaw's, one of those two, was even kind of come up with as a concept. So like we have a very limited number of these algorithms to even play with. The big players are building these things. IBM, Google, they've got systems that do these things. The physical challenges. I don't know how it compares to, say, fusion, but they're big engineering, like real engineering, not our engineering problems. I think it's going to change. I think there are, I mean, even if you say like maybe you're a bad actor and you want to break all cryptography in the world, that's a pretty interesting thing to invest time and energy and money in. So maybe you're a good actor and you're a nation state and you're trying to do some of these things. I think there's some interesting problems to be solved here. What does quantum algorithm, quantum encryption look like? I think it's good to be thinking about it.
One last question, and that is probably my favorite one because it also nicely introduced our next speaker, and the chat just moved. Community layout shift is still a problem in web. So, Craig, which quantum physics degree did Alex just get? And can he trade one with you for a V Plus license? Alex, did you see what I just did there? Big brain move right there.
Right.
I am 100% available and certified to shake any hands and hand out any diplomas that anyone wants me to. I'll smile and wave. I think this is level 1. So let's keep learning and keep getting to doctorate level of this stuff, I guess.
Love it. Craig, thank you so much for joining us at 2:45 a.m. in the morning for this talk. I could not appreciate you anymore. And I hope we see you again very soon, sooner than later.
Appreciate you too.
Thank you.
Have the best day. I'm going to go to sleep. Enjoy JavaScript day, everyone. It's already Friday here, so whatever.
Thank you.